Okay, let me just say then a couple words before that. As usual, well, welcome to the talk series, and as we usually do, we are recording this talk, and per the speaker's request, it's going to be published on YouTube. I believe you signed this form, Eduardo?
Yes.
Yeah, so of course no internal questions, anything like that. If someone has some kinds of sensitive questions that you don't want to be recorded, we'll give an opportunity for that at the end of the presentation. Also, just for everyone's awareness, these cryptography talk series talks are always announced on the Cryptalk alias, so some of the people who are joining might not be aware of that. So that's a Cryptalk distribution group. Feel free to join, and we'll get these announcements. I think with that, Patrick, go ahead with the intro.
Yeah, we have the signal to start?
Yeah.
Yeah. All right. Hello, everyone. It is my great pleasure to introduce today Eduardo Persichetti. He's an associate professor at Florida Atlantic University and an expert in code-based cryptography. He's been working very actively in the NIST Post-Quantum Cryptography standardization process with multiple submissions, but the most important one maybe it's called HQC, which was recently selected by NIST for standardization. And this is going to be the main focus of this presentation. So with that, please, Eduardo, the floor is yours.
Thank you, Patrick. I want to start, well, very briefly, thank you for the invitation. It's a pleasure for me to speak at Microsoft again. I regret not being able to be there. I visited Microsoft years ago and I gave a talk in person, and well, now here we are, but it's still a pleasure. So yes, HQC, it's short for Hamming Quasi-Cyclic. And it's my pleasure to present it. This was recently announced by NIST at the end of the 4th round. So here's my plan for this presentation. I will give a little bit of background so to ensure that we are on the same page with regards to the mathematics at least. I will present the HQC design and the rationale behind our proposal, and then briefly discuss some security aspects which are kind of paramount as well in the design, and explore some parameters and briefly discuss performance of the scheme and draw some conclusions. So you're welcome to interrupt me anytime if you have questions. Otherwise, I'm sure we can have a discussion at the end. So background, like Patrick said, I mainly work in cryptography related to coding theory, as my background is from coding theory. So here's a quick refresher of what coding theory means, at least for us interested in cryptography. So linear codes are essentially vector spaces of a certain dimension inside a finite field. And n is called the length of the linear code, and k is its dimension, and r, which is the ratio between dimension and the length, is, if you want, a measure of effectiveness of the code, and is what we call the code rate. Okay, so typically r is some fraction close to 1/2, but it doesn't have to be. Huh? And at least the codes that were used most commonly are measured in the Hamming metric, which is a very discrete type of measuring. So it simply counts the number of non-zero positions. And so in this metric, we're able to define a notion of distance and weight, with the weight being exactly the number of non-zero position and the distance being the difference between the two words. And then once we have a distance, we can define a notion of distance of a code, which is the minimum among the distance of all the code words in the code. So it measures how close the code words are to each other in the code. And so we refer to a linear code as an NKD code, with 3 parameters kind of classified. And these are very important because it's what allows a code to actually do its job, which is encoding and decoding. Right? So codes being vector spaces, we can represent them as vector spaces get represented usually, which is as with bases, right? So we traditionally take basis vectors as row vectors, and we can put them in a matrix of size k by n, where k is the dimension, n is the length. And so we call this a generator matrix because it generates a code, as you can see, essentially as a basis does, by doing linear combination of the basis vectors, right? So we have each code word is associated to a specific linear combination of the rows. This linear combination being the vector m, which we think as a message that gets encoded into the code word C. Of course, this being a basis is not unique, so we have several choices for bases that we can obtain via change of basis, right? So these square invertible matrices S give me different bases for the code. And in particular, there always exists, or almost always exists, a choice for generator matrix that has identity on the left corresponds to a specific choice of the change of basis matrix S. This is not the only way to define a code. Sometimes we like to think of codes as kernels as well. And we use the other matrix, which is called parity check matrix, which is kind of a historical name. It's associated to the original formulation as checking the parity of the code words. So this is a matrix of dimension n minus k by n, and it classifies the code as the set of vectors that satisfy this equation h times c equals 0. So like I said, as a kernel, in particular, this vector h times c is called the syndrome of C because as a medical term, right, it gives kind of the syndrome, it gives the details of what's happening with the word. And if the syndrome is 0, then we know this is a code word. And if the syndrome is not 0, then this is not a code word or some error has occurred. So like generator matrix, although for a different reason, parity check matrix is not unique. We have several choices that can be obtained via invertible matrices. And we also have a notion of systematic form for parity check matrices. Okay, so this is kind of the ABC of linear codes. They're vector spaces comprised of several code words. Each code word corresponds to a specific linear combination, if you want, to a specific message, and they are at a certain distance from each other. And all of this comes into play because codes originally, right, have the purpose of encoding information over a noisy channel and correcting a certain amount of errors that may occur. So we say the codes are W error correcting if there is an algorithm, the code, that is able to correct up to this many errors. And so how many errors depends on, well, the infinite, if you want, the theory of codes, right? The large coding theory. There are several different types of codes, and each of them has a specific methodology and reason why it's able to correct errors. However, if I don't know the specific type of code, then I'm dealing essentially with a random code. Right? I can always do this. I can get a bunch of linearly independent vectors, put them together and get a random generator matrix, for example. And then actually to decode errors is hard, right? So we have this problem, which is very well known. It's called the general decoding problem. And if I give you a generator matrix without any structure, without any hint of how the coding algorithm may work, and a target weight, and a code and a received word in the space, I should say, a word Y, finding the close code word in the code within this radius is the problem, and this problem is hard. In fact, we can formulate it with the parity check matrix as well, which is called syndrome decoding problem, since we are now dealing with syndromes. And so instead of giving G, we give an H, we give a parity check matrix, and we ask to find what is the error vector that gives a specific syndrome. Okay, so it's very easy to see that these two problems are equivalent. For the people who know lattices, right? The decoding problem is kind of what people think about as LWE, and the syndrome decoding problem is what people know as short integer solution, right? So here we have a solution which is short in the sense of low Hamming weight, right? So we have to have a bound on how many errors we are trying to correct. So this problem was proved, in fact, to be NP complete. back in 1978 for the binary case, and then generalized to the QRE case in 94. So SDP is MP complete, and GTP is a completely dual version of it. So it's a very strong foundation to build cryptography on. The solution is unique when the number of errors that we're trying to correct is below a certain threshold, which is a combinatorial threshold. We don't have to spend too much time on this, but essentially we have a bound on the size of spheres in the space. So when we are within this bound, we guarantee that there exists only one word with that weight. Okay, and if we try to solve this problem, like I said, we're doing it for a random code, then essentially the best type of attack that we can do, and we'll talk about it later, is what we call information set decoding, where we try to figure out an information set in the code, in the matrix that we're given, which is a set that carries all the information symbols, that is free of errors. And so it's kind of like a glorified search algorithm, if you want. With all the frills of the situation, we can do many improvements with birthday paradox, etc., etc. But essentially, we're still kind of trying random columns, yes, if you want. But we'll talk about this a little bit more later. Okay, let's get to HQC. What's the idea behind HQC? So for many years, code-based cryptography was seen as using the decoding algorithm as actually the private information, right? So I have a code that I know how to decode, and then I want to disguise it so that the public cannot decode in this code, right? So this is kind of the idea. So I can obtain a trapdoor in this way, right, by disguising a private code into a public one, which is kind of very natural thing to do in public key crypto. For example, the ML-KEM crypto system, which is kind of the flagship of code-based cryptography, right, the progenitor of all other schemes, or the Niederreiter version, which is based on the parity check matrix. Anyway, like we said, these are kind of dual of each other. What it does is it starts from a private code that is decodable, efficiently decodable, and then it disguises it by changing bases and scrambling the matrix via column permutation and obtain an equivalent code. But this now has no recognizable structure anymore. So there is a difference between a private code and a public code that is no longer recognizable. And the big difference is that in HQC, we kind of remove this aspect, and the decoder is now public. So we use the decoder as a method to remove errors, and the trapdoor is no longer this difference between the private code and the public code, but instead the trapdoor is just a mask that we put on top of our plain text. Okay, and the decoder is public, but only works if I'm able to remove the mask, because it otherwise has the weight that's too high and it doesn't work for very short. But again, we will see this exactly, but this is just to give a high-level overview. And so to actually form the ciphertext, we use an inner code, like an unrelated to the one that we used for decoding, for correcting the errors. So you see, we have like now kind of separated the tasks. We use one code for creating the ciphertext and one to remove the errors. And now this inner code doesn't actually need to decode anything. So it can be an entirely random code. And in fact, we can choose it in a way that is convenient. So we can use this quasi-cyclicity so that the process of generating the ciphertext is more efficient and the ciphertext is more compact. So with this, it's kind of like a very different approach to how code-based cryptography was always thought of, at least in the context of encryption. So what does it mean, quasi-cyclic? Let me clarify this. Cyclic codes are very well known in coding theory, as we can start from there. Essentially, a code is cyclic if it's invariant under cyclic shifts. Right? So that means that if I take a code word, then all the shifts of the code word are also part of the code. So it's a very specific type of code, very powerful, right? And this we can easily represent with circular matrices. Quick refresher: circular matrices is a matrix that contains all the rotations, right, of the first row. And so an interesting property is that mathematically these objects are isomorphic to polynomials, right? So the ring of circular matrices is isomorphic to this polynomial ring, fq of x, quotient with x to the n-1. So these are polynomials of degree n. And so now we're kind of moving away. So we have this kind of interesting formulation in terms of polynomial, right? So then every code word is in fact a polynomial. And we can simply say that a code is cyclic if x times c of x is also a code word, right? For whatever code word. So we get quickly all the cyclic shifts. Okay, once we have this, and cyclic codes, like I said, are a very important family inside the coding theory, we can relax this notion a little bit, right? We can generalize it, and we say that a code is quasi-cyclic if not necessarily all the shifts are also code words, but just the shifts up to, say, a certain power r. Okay, so we have different kind of orders of quasi-cyclicity. So this leads to matrices that are not fully circulant, but maybe only block circulant. Yes, but you can see that this generalization is very natural. In our case, we focus on the binary case. So these are not only polynomials, but they are actually, in fact, binary polynomials, very easy to operate, just coefficients 0 and 1 with binary arithmetic. And we use two block quasi-cyclic code. So the simplest case, yes, just two blocks. So a parity check matrix is simply given by two polynomials, h0 and h1. And you can imagine that these two polynomials each generate their own circulant block, yes? And once we have a parity check matrix in this form, in fact, it's very easy to compute the systematic form. We just need to invert the left polynomial, and we get 1, which is the polynomial 1, 0, 0, 0, 0, which gives me the identity block when I take the circulant block, and then h0 inverse times h1 inverse as the rightmost block. And this is a parity check matrix for a two-block quasi-cyclic code binary. Okay, so this is the kind of object that we would be operating with very simply. And you see that it's very easy to generate. You just need to generate two polynomials, and then well, in fact, we directly generate the polynomial h, since this is a random code, right? So this is what I'm going to be doing. For convenience, we're just going to drop the dependency on x. These are polynomials. We're not going to call it h of x every time. And I'm going to indicate in red the private data, and in green the public data, and in blue the one-time randomness that is used in the scheme. So what's an HQC public key? Like I said, we have a public code that we use for removing error purpose, for the decoding. And then we have this quasi-cyclic code that we use to actually manipulate the objects. So capital G is the generator matrix for this public code. And then H is that polynomial that gives me the circulant block, that gives me the parity check matrix for my quasi-cyclic code. Then I sample a random pair of vectors, x and y. Together, this will form a word, right? Both of these vectors have Hamming weight w, so within my threshold. And if I compute x plus hy, then I obtain essentially the syndrome of this word xy. Okay, so my private key, like I said, is this xy pair. You can think of it as a word that is a mask, that would be used as a mask. And then the syndrome of x and y is a public key. Okay, so you see a big difference. Like I said, the public key is not now the description of a code, but is rather a mask. So how do we encrypt? We take a plain text, which is a polynomial in the same ring. And we sample some randomness. Specifically, we sample a vector E with a specific weight WE, and two more vectors R1 and R2 of weight WR. Okay, so all these objects are one-time randomness. We will use it to hide things. And then we compute the ciphertext, which has two pieces. The left piece uses the public key, is the syndrome of R1, R2, essentially. And the right piece is the one that actually contains the plain text. So we encode the plain text in a code word in the public code, and then we cover it with this error vector, which is S times R2 plus E. Okay? And so these are ciphertext. And you see that essentially the part containing the plaintext is the right part. The left part is going to be used to carry information that we can then use to remove the mask.
Eduardo, can you hear me?
Yes.
Question. So, do you like concretely in the implementation, are these really represented as polynomials then?
They are represented as binary vectors, right? Because there is this easy bijection between the polynomial and the coefficient. But then, of course, the arithmetic is polynomial arithmetic, yes.
And so the polynomial ring here, when you have this like block form,
yes.
What's that ring?
So the ring is going to be this one, right? It's just going to be F2 modulo x to the n-1.
Okay, I see. But if it has this like block cyclicity, is that how is that the correct one?
So you can imagine that each block, in fact, is each block is like a square circular block, right? And you have like two of them next to each other, but like they operate like each block is essentially corresponds to a polynomial and operates with polynomial arithmetic.
Oh, okay, I see.
Right.
Yeah.
So the whole range of operation is in the polynomial ring, and in fact, this is why I present the scheme completely losing the reference to matrices. At this point, we don't really want to think about matrices anymore. Like if you want, in the back of your mind, you can think, yes, this is the syndrome, etc. But like you're just really multiplying polynomials with each other and adding them all inside the ring.
Okay.
But good question. Thank you. So this, of course, this means also that we have this kind of polynomial arithmetic in the ring, which is very efficient. Yeah, this is kind of one of the advantages. Okay, so the decryption process actually is very simple. It can be summarized as follows. We just take the two parts of the ciphertext, V and U, and then compute V minus U times Y. Remember that Y is part of the private key, and then we just apply the decoding algorithm. Okay, and so we can go step by step in this. So when you compute V minus UY, remember that the right part V contains the code word plus this mask SR2 plus E. You are now going to multiply the left, which was R1 plus HR2 times Y, and do some algebra. So now you remember the S was the public key is X plus HY times R2. And you can see that there's a term that cancels out. Right, there is the term HYR2, which cancels out with, well, this should be minus, obviously. Sorry for the typo. So this term cancels out, and then you're just left with MG plus XR2 plus E minus R1Y. Okay. So always check your arithmetic because I did a typo here, but anyway. So we have this error term here. So we get a code word plus an error term. But now this error term is only like sparse multiplicative terms, right? Because we know that X, R2, E, R1, and Y all have like a weight within a certain threshold. And this threshold is going to be chosen so that the total weight of this part, let's write this as like mg plus E prime. Okay, so all this red and blue part is just like a big error polynomial vector. Okay, we just need to bound this to make sure that we're able to decode it, because then this is what kind of we feed into the public decoder. And if this is not below the decoding radius, then we have a decoding failure, right? So of course, we want this to essentially never happen or almost never happen if we are doing decryption correctly. But like I was saying at the beginning, if I don't know what the private key is, then I'm stuck with something that is way beyond the error correction radius. And the difference is that when I see the term V here, mg plus SR2, now this S is not a low weight polynomial, right? So this is going to be high weight and completely cover the code word. Okay, so there is this difference. This is why I was saying at the beginning, the decoding is only meant to work if I'm able to remove the mask, and then this kind of leaves a low weight error vector. So it's important to understand what error distribution is for this term, for the term E prime, right? And so these are essentially Bernoulli distributed according to a certain probability parameter P star. And this can be calculated exactly. And we do it, of course, in our work. Here, I'm just going to try to give an intuition. If the coordinates are assumed to be independent, it seems a reasonable assumption. Then the weight of E prime follows a binomial distribution, and the probability of the weight being equal to d is exactly n choose d, p star to the d 1 minus p star n to the n minus d, which is the stereotypical, if you want, binomial distribution, right? And d is going to be certainly greater than 0, greater than or equal to 0, and bounded above by 2 WWR plus WE, which is the maximum, the worst case, right? A combination if you take the weights of X, R2, E, R1, and Y, or N, right? Minimum of these two. All right, so this is kind of like a first glimpse of what we can expect from this term E prime. We ran extensive simulations. We'll talk later about bounds. But essentially what is important at this point is that we have a very solid bound on the possibility of a decoding failure happening when it's not meant to happen. Okay, so if we're decrypting correctly, then this decoding failure should almost never happen. And we'll make sure to bound that. Okay, so hopefully the encryption and decryption process makes sense. We take our plain text, we put it in a code word, we hide it with some high weight error on top, and then we use the left part of the ciphertext to remove this mask using the private key. Okay, so this takes us to security, and maybe some of you are asking, like why start with the PKE? Well, we start with the PKE because this is kind of the starting step, and this is very easy to verify. Is an in-CPA secure encryption scheme. The proof is very simple, and the security of this in-CPA secure scheme is based on a variant of the syndrome decoding problem that I presented at the beginning. So the idea is still, given a syndrome, recover the vector that comes from it. Except that we're claiming here in the CPA security, so we're not really actually trying to. So we're trying to distinguish, which is, if you want, like a stronger goal, right? We want to be secure even against distinguishing. So the problem that we're basing ourselves on is the decisional version of the syndrome decoding, and because we are in a quasi-cyclic code, this is not a completely random code. It's a random code in quasi-cyclic form, right? So with this kind of characterization, this is essentially still the syndrome decoding problem that we're based on. Okay, and then at this point, once we have an encryption scheme, it's easy to obtain a KEM from it. This is what every candidate in NIST essentially ended up doing, right? I remember in round one we had a lot of schemes that were actually kind of presenting themselves as an encryption scheme, but we all kind of quickly realized that the thing to do is you start from an encryption scheme, and then essentially you can get a KEM out of it, right? Via what is now absolutely standard means, so some flavor of Fujisaki-Okamoto transformation. And in fact, in our case, since we start from an in-CPA secure scheme rather than a one-way secure scheme, there's even a tighter reduction that we can exploit. So we use the HHK framework of Fujisaki-Okamoto for the people who are specialists in provable security. This is one specific, very nice formulation of Fujisaki-Okamoto, very nice modular formulation. So the steps to obtain such a KEM are very simple. We de-randomize the protocol, right? So rather than sampling randomness every time, we just obtain the randomness as a function of our input, right? So now we have a deterministic PKE. We then transform it into a KEM with implicit rejection. So this means that if there is a decoding failure, if the decryption fails, we actually do not return fail, but we return a pseudorandom string that we obtain via some pseudorandom part of the private key. And then we incorporate, the additional protections that are also kind of standard at this point. For example, SALT to prevent multi-target attacks, and similar protections. Okay, so this is kind of the blueprint, which is standard, like I said. So the interesting part, at least in my view, is the underlying PKE is a strong PKE, is an in-CPA secure PKE, and then the transformation into a KEM is essentially routine, with our decision to utilize implicit rejection, which is also kind of at this point accepted in the community, I would say. And okay, so like I said before, we have not the standard syndrome decoding problem, but we have a variant of syndrome decoding, and so there is a little amount of things to keep in mind. For example, since our code is quasi-cyclic, this kind of gives an advantage to the attacker, because he knows that there is a correlation between several vectors. They are shift of each other. So there is this attack called Doom, which exploits this, and it gains kind of a square root factor, but it doesn't substantially modify the security baseline. Of course, since this is a decisional problem, there could be trivial distinguishers. So we have to account for parity of the syndrome. So essentially, we append 1 bit at the end. We lose 1 bit of security. But again, this is not really breaking the bank. But after all these kind of considerations, essentially, the security reduces to the security of breaking SDP. So maybe now we should talk about what is the security of breaking SDP in a few words. So like I said, the best generic decoding attacks are those in the information set decoding family, which is essentially a glorified kind of search for an information set free of errors. So this is an algorithm that was initially due to Prange in 1962, and the complexity is exponential. You can see in the number of errors, W, as well as the code rate, which is kind of the quantity to keep in mind here. So not necessarily the code length, but actually the code rate. And C Gauss is just cost of Gaussian elimination, right? Because what we do at every step, we pick, if you want, a candidate information set, row reduce according to that information set, see if we get any errors, see if the syndrome matches, if our guess was lucky, and if it's not, we just try again. Okay, so this depends on how many errors we are searching for and how lucky we are in picking the columns. And since then, we've had...
Eduardo,
yes?
What is ISD?
So ISD is short for information set. So information set decoding. So information sets are a particular subset of the columns, right? They carry the information symbols that are free of errors. And so what the information set decoding does, like I said, is you try to guess one such set of columns. If you guess right, then you're immediately able to invert the word and find the errors.
All right, thanks.
Yes, so it's a search algorithm, right? It's a probabilistic search algorithm, which essentially, like I said, of course, one can apply the usual improvements of birthday paradox and looking for certain specific things, but writing lists at the cost of memory, etc., etc. But at the base, what it is that we're randomly searching for a set of columns that doesn't carry any errors. And as you can imagine, this depends on how many errors we're searching for, and so this is why the complexity is exponential in W, for example. Right. So to show you kind of an overview of the work since 1962. There has been several works on information set decoding that try different techniques to perform this search, and this list is not exhaustive. Okay, and the common characteristic is always that the running time is essentially 2 to the W times a constant that depends on the code rate and the error rate, W over N. Right. So this is kind of important because when W is ON, then asymptotically, this constant is essentially the same for all algorithms, which is negative log of 1 minus R. And so this means that improvements to the original Prange algorithm are only polynomial in N. So you can gain a small amount, but it's not substantially going to change the nature of the algorithm. We're always going to have It's essentially there's very similar complexity. Yes, you can lose a few bits, 2, 3, 4 bits, but it's not going to become suddenly a much faster algorithm. So this is a very strong argument for security. Right, so this is not to say that all these many papers, and I think many of them have landed in prestigious venues, right, Eurocrypt, etc. It's not like they don't do anything, but they don't change the nature of the attack. Okay, so with this in mind, we know that we have a very strong basis for security. So how do we choose parameters? Right, so like we see, we kind of decoupled the two tasks of correcting the errors from encoding. So this public code is just required to correct the maximum amount of errors possible in the best way. So it can be chosen for maximum efficiency without regarding security. And on the other hand, what we already saw before is that the code, the quasi-cyclic code that we use to actually create the ciphertext, doesn't need to decode, so it can be chosen just for security. This is why we choose a random code and not like other schemes. We are using a GOPA code or an MDCP code or other codes that we have to hide. Right. So hopefully this is clear, because this is kind of really the main point. We have one code that can be chosen just for security, and it can be completely random because it doesn't need to decode, and one that can be chosen just for efficiency. So maybe now we can talk about the code for decoding. In our initial proposal, we had this kind of tensor product of a BCH code and a repetition code. And then we switched to a new formulation, which is more efficient overall. There was a transition. There was, I think, in round 2, we had both proposals, and then we figured out that the second construction was just plain better, and then we stuck with that one. So now we use a concatenated code, which is a concatenation of a Reed-Muller and a Reed-Solomon. So I don't want to go too deep in the coding theory, but essentially, a concatenated code is what the name says. There's an outer code, an external code, and an internal code, right? And when we encode with such a code, we take our message, we pass it through the external code, and then this becomes a series of code words for the internal one. So it gets kind of encoded twice. We use a bijection, right, from Q to the KI, and we obtain a code which has length and dimension equal to the product of the respective ones, and the minimum distance, importantly, is also the product of the two minimum distances. So we amplify, right, by a lot. This is kind of what's happening. I don't know how big you can see the picture, but essentially we start from a message, we pass it through the external code, we get a code word, right? We go from, say, length 3 to length 4, right? Then we take each element of this code word, which is like an element of FQ. This becomes a message in the internal code, and then we encode that with the internal code. We do this for every element, and we get this kind of concatenation. And this is our final code word. So the final code word will have a length, which is the product of the two lengths you see here. So why do we do that? Because then the internal code can be extremely powerful, right? Like can use a maximum likelihood decoder, and the outer one is traditionally like one of these algebraic codes instead. And once we do this, then the overall decoder is polynomial time, right? When you decode errors, you decode them inside out, and we get an exponentially decreasing failure rate, which we are able to study very accurately. So our choice for the external code, like we said, is a Reed-Solomon code, which are kind of a very famous, perhaps the most famous family of codes, or one of the most famous family of codes out there, over F256. In fact, we don't use exactly Reed-Solomon codes, we use a shortened version of Reed-Solomon codes that can be decoded with an adapted version of the same algorithm, right? So Reed-Solomon codes are decoded traditionally with Verlekamp algorithm. There are standard algebraic decoders for these. We just shorten them by we're able to decode them pretty much the same way. For the internal one, we take a Reed-Muller code, which is again a kind of standard construction from coding theory. So this RM17 is what we call a first order Reed-Muller code, which has length 128 and very, very low dimension. So see, like this is kind of an extreme code and very high minimum distance, 64. and then we duplicate it, as in we duplicate the bit, we just repeat it according to security category. And this can be decoded via fast Hadamard transform. So again, it's a very efficient decoding algorithm. This is kind of the choice of codes that we use in the 3 different sets. For example, for the first set, HQC 128, which is the category 1 set, we start from a Solomon code of length 255 and very high dimension. And then when we go to the shortened one, you see it preserves the minimum distance. So we just chop it off. We preserve the same minimum distance. For the internal code, we start from the first order removal code and we take multiplicity 3. So we triplicate each bit. And we get to this code that is long 384 with the same dimension and 3 times the minimum distance. So we do this so that we obtain extremely efficient decoders. And similarly, we proceed for category 3 and 5 parameters where we take multiplicity 5 for the internal code. And this is, a little bit of coding theory, but essentially this is kind of the meat of the scheme, is that now we have an extremely efficient decoder. And what's most important, we know how these codes behave very well. For example, for the internal code, a very simple upper bound is given by this binomial formula, right? This depends essentially on the transition probability of the binary symmetric channel. Remember, this is just a binary code, the internal one. We can improve it with a bit of work. I don't want to go too much into detail. Of course, we have like the full analysis in our work, but this is like a tighter bound. And once we combine this, we can confirm our bound with simulations. In fact, our bound is even conservative. You can see here that for the category 1 code, remember this is the internal one, right? The first order removal code that is triplicated. We get a failure rate of 2 to the minus 10, roughly, from the bound. 10.79, and in fact it's 10.96, the one that we have confirmed through simulation, so it's even a little lower. And similarly for the other parameter sets. Okay, so this is just the failure rate of the internal code. Like I said, we combine this with the outer code, with the external code, and we get an aggregate formula for the total decoding failure rate, which depends now, you see, on the external length, NE. And PI is the probability of the internal one failing. So this ultimately is the formula that we use to pick the HQC parameters. We want this decoding failure rate to be negligible, and in particular, it needs to be below the claim security level. So for the first set, category 1, we want this to be below 2 to the minus 128, for example. So this kind of brings me nicely to parameterization for the scheme. The public key, if you remember, the description of our encryption scheme is just a single syndrome of length n, where n is the length of the code. And remember now the code is going to be the external and the internal, and you multiply. The private key is just a single seed. Of course, this is entirely random, right? It's just a random mask, so we can compress it down to a single seed. And the ciphertext is a pair of polynomials, a pair of vectors of length n in the code. So putting all the previous information together, we have, remember, the length of the code word is going to be the product of external times internal. So here we had the length was 46 for the first one, and then 384 for the internal one, right? So it's 46 times 384. We get 17,069. This is a very, very long code, right? And we have 66 for the weight and 75 for WR and WE, which are the weight of the masks. So almost the same. In fact, WR and WE do not need to be the same, but they're chosen identical. This makes the analysis simpler. And this chosen parameter results, as I was saying, in our desired, in our target DFR, which is negative 2 to the minus 128. And similarly, we parameterize for category 3 and 5. So it's very simple. It's very easy to choose parameters right? Once you have a target in mind, because you have a very clear analysis of what the DFR is, right? So here we have these lengths with weights that are not much bigger, and they yield the correct decoding failure. And then these are the resulting sizes. Like I said, the private key is extremely small because it's just seed. Here we have sizes in bytes. The category 1 parameters are about 2 kilobytes for the public key and maybe double that for the ciphertext, which makes sense because the public key is just one vector of length 10. The private key is 2 vectors of length 10. And then it scales kind of nicely with the security category. So we're in the range of like a few kilobytes. As far as measurements go for performance, we have a reference code, which I think from now on will not really be relevant anymore. This was kind of for NIST purposes of explaining the implementation. So now we have produced a fully optimized AVX2 implementation that runs in constant time to prevent timing attacks and such. And the timings are about this. So we have maybe like just below, well, 75 kilocycles, just a few hundred kilocycles, let's say overall, for our parameter sets. If you this kind of ballpark, typical ballpark. We also have at least one hardware implementation that I'm aware of on RTX 7 that is available, which is kind of rather compact in terms of areas. I should say I'm not an expert in hardware implementations, but it's a nice portable implementation with very fast key generation, which is kind of important if you are looking to use these as a, for example, mechanism inside TLS or other ephemeral key transport mechanisms where you have to generate keys every time. So in conclusion, I think the motivating factor for NIST was the confidence in HQC's security. This was kind of a big difference with the remaining candidates in the NIST competition. Bike was the competing candidate with a very unclear DFR situation compared to HQC. Classical is following the kind of traditional approach with algebraic codes. So different ballpark, and the HQC security is linearly clear. So we have an accurate DFR analysis. We have a rigorous NCCA proof with the steps using Fujisaki Okamoto, as I've detailed before. And we have a tight reduction to a well-studied problem, which is this variant of SDP. So this kind of was our trademark, if you want, in NIST size, and I think this still is our trademark. In terms of performance, and now you may be familiar with Kyber, now ML-KEM, which of course is very fast and a little bit shorter, right? So we're kind of one step behind, but we still offer a very good bandwidth and latency, all things considered. Like I said, we were ultimately preferred to competitors. It's very recent news for us, but I believe that despite the performance penalty, right, like Bike, for example, has shorter ciphertext, mainly due to our security aspects. So the idea of NIST is to standardize as secure an algorithm as possible in this case. And HQC, in the end, is a balanced scheme, doesn't really have any real weaknesses. I think is very suitable as a general purpose CAM, which is the intent behind ML-KEM. And this is certainly the hope for us, is that we will see it as a general purpose CAM in various situations and applications. So I thank you for your attention. I'm happy to take questions.
Thank you very much, Eduardo, for the very nice presentation. Are there any questions from the audience? Satya?
Yeah, very nice talk, Eduardo.
Thank you.
I have, maybe you said this, but I made a mistake. Why quasi-cyclic? Why not just simple cyclic codes?
Quasi-cyclic is the standard for security because a fully cyclic code is very easy to recognize. So so quasi-cyclic is the next step down, essentially.
I see.
Yes.
And sorry, one follow-up question. How do you choose W
So
to wait for the syndromes? Yeah.
yes. So this is chosen based on our DFR.
Okay,
And the hardness of information set decoding. So we have this kind of where am I? Here, where you see the kind of the running time for information set decoding. This depends on the most suitable version of. Right now is the 2022 algorithm. The other ones are mostly quantum versions, etc. But so you kind of parameterize for this information set decoding to be 2 to the 128 or whatever kind of category you want to reach. So all you need to choose is just the weight, right, and the code rate, and the rest kind of follows.
Sorry, I don't quite understand. So you want W to be as large as possible, or as close to minimum distance as possible, or small? Because for DFR, you want W to be as small as possible, right?
So you want W to be yes. So you want it to be small, but you also want it to be as large as possible within the decodable radius.
Right.
Because larger W means harder attack.
Right.
So you kind of push it to wherever the limit is in terms of decodability.
Okay. All right. Thank you.
Makes sense. Thanks.
Hey, Eduardo. I have another question.
Hello.
Hi, good to see you. Thanks for the great talk. I have a question about bike. You said the security picture was a bit unclear. Can you quickly say something about the differences? Because they use quasi-cyclic codes too, right?
That's correct. Yes. So the main difference between our work and bike is that bike is based on a quasi-cyclic code, which is also the same code that is used for decoding. So what this quasi-cyclic code is a low weight, is a low parity check code, moderate density, I should say, is the correct term. And so this has a specific decoding algorithm that comes with it. And so what you're trying to do is you're doing two things at once, right? So you're trying to use this code to correct as many errors as possible, but also you're trying to use it for security. And so you're in a sense the analysis of the failure rate for this code is not as clean as the one that we have for the public code here. So we have a result which is based on simulations for bike, and it's an extrapolation method, right? So the main difference is that the DFR here depends on this public code, which is extremely specific, right? Like we saw, is like is this very basic with Muller code, which is triplicated, so it's very easy to analyze the DFR for this code. But for disguised MDPC, it's not so easy. You have to use Markov approximation, etc. And in the end, the security analysis is not so clean in that case.
Thank you.
This is why, yeah.
And then with respect to classic McLeese, for example, so you said NIST was picking for security. Would you say that classic McLeese would have been more secure, and there was just at some point, the sizes of keys were just too bad, or
Yeah, this is a really good question. So I personally am part of the McLeese project, so I absolutely believe in the security of McLeese. It is true that essentially it's an algebraic code, right? It's a GOPA code, it's a binary GOPA code that is hidden in a rather simple way too, right? It's just a standard way with change of basis permutation. Now, this has resisted security for many, many years. We are absolutely confident in its security. I don't think this is the reason why NIST did not, in the end, decide to standardize it. The size is definitely a consideration. I believe that the NIST primary goal was to have as close to a silver bullet as possible, right? So one, a general purpose KEM. We are seeing some interest in McLeese in certain specific scenarios. I think it's worth investigating. In certain scenarios, it may be a solution that is interesting. The ciphertext, for example, is very small, and the scheme is very fast, faster than HQC and Bike, and so it's just an extreme corner performance-wise, right? So maybe NIST did not have the resources or did not want to allocate the resources to the standardization process. We are not quite sure, actually, what their rationale is, but it's not a security issue, I don't think. I think we are absolutely confident in the security mechanism.
I was just asking about how you compare it to HQC. It's difficult, probably, right? You wouldn't say it's more secure, or?
I mean, HQC uses random codes, so it's a different ballpark. In a sense, with ML-KEM, you have to do a leap of faith in the security, like you do it for many other crypto systems that have been used for years. Yeah. Right, like discrete logarithms, and but we are confident in the security. It's just, I mean,
yeah. Thanks.
Any other questions? If not, I have one more question. I also had the question about Bike, so thanks for the explanation. So now that the process is going ahead with the HQC, are there any discussions to change anything in the KEM? Anything that NIST is probably suggesting, or they are happy with the design as is?
I think NIST is overall 99% happy. There are some minor glitches in the code, but the design is not going to change. And after that, NIST will write their FIPS, and I think the final design is the KEM design with implicit rejection as it is. Like I said, maybe we need to move the salt from one side to the other, or very small things, but the design is the one that I showed you. In fact, I didn't show you. I showed you the underlying PKE, but after that, it's kind of standard transformations. There will be, I expect, little tweaks, but nothing major.
All right, similar to ML-KEM probably then.
Exactly. Yes, this is what I expect.
Small
maybe
jump with some tweaks here and there.
Right. I don't know. Include the public key in the hash, or kind of small things which maybe make it better for side channel or other things. But I expect, in fact, a very similar process to what they did for ML-KEM standardization.
All right. Any other questions before we close the presentation? Well, if not, I want to thank again Eduardo for the kind, for accepting the invitation, or for giving us a great presentation. So thank you very much, Eduardo.
Thanks, thanks everyone.
Hope to see you soon.
Yes. Will be. I always travel for various conferences, and I'm hoping to catch you around.
Yeah, for sure. Thank you very much, and thanks everybody for attending this presentation. All right.
Thanks for having me.